in in the area of wide bandgap semiconductor device-based power converters in IIT Delhi. Okay. So first of all, the outline for the presentation is, first of all, I will discuss the renewable energy in India and silicon carbide and gallium nitride semiconductor-based technology, an overview of that, and the resonant gate driver for silicon carbide MOSFET, which we have developed in our lab, and a controller for SiC MOSFET-based grid-connected converter. So, so as all of us know that renewable power generation, we have solar, wind, uh, small hydropower, and biomass, and the total power generation from renewable is 71,500 megawatts in July 2018, and it is rapidly growing. And the prediction is by 2022 we should have 175,500 megawatt power generation, and out of this 57% 57% should come from solar, while currently we have only 33% from the solar. So solar power, Indian government is putting a lot of stress on the solar power, where we have concern about efficiency. Efficiency of the power converter used for solar power generation should be very high. So so we had solar installed capacity 6.76 gigawatt during 15-16. It has doubled in 16-17, and by again 30th June 2018, it has reached 23 gigawatts. So solar installed capacities are increasing, and the trend is the same. It's almost doubled every year. And so basically, when we have the renewable energy source, basically we are replacing the power generation from synchronous machine to power converter. Synchronous machines are getting replaced by a power converter. So power converter are supposed to function as a generator, and the main concern of the power converters are they should have a very high efficiency, very high power density, and very high reliability. And to achieve these for efficiency and power density wise, wide bandgap semiconductor technologies are very important. So typically wide bandgap is more than 3 electron volt compared to silicon, which has 1.1 electron volt. This will ensure that the RDS on, the drain source resistance, when it is on, it is less in case of silicon carbide or gallium nitride based technology. So this yield a low conduction loss. Then these devices have low parasitic capacitance, so it means it can switch very fast. If this can switch very fast, then which in turn means that the switching losses are low. And these devices are majority carrier devices, so problem related to reverse recovery of bipolar devices, PN junction, is avoided in these. So these are very few of couple of advantages which we have in silicon carbide and gallium nitride technology. And but what are the challenges if we use these devices? If we use these devices, we'll get a very high efficiency, very high power density. But what are the challenges? The challenges are, because of high switching transient, it is very difficult to design the circuit around it. Yeah, we should have a very reliable protection circuit, very good packaging of the converter and its associated circuitry. Then these devices are new, so not much experience from the company, from the industry is available to us. So how to design for reliability, that is again an issue. and what should be the switching frequency and the heat sink for minimum loss and minimum volume. Everybody says that you should switch at megahertz or hundreds of kilohertz, but what will be the optimal switching frequency at which you will get the minimum loss and minimum volume? So that needs to be found out. Uh, so we have worked on the silicon carbide MOSFET-based circuit. So we developed a double pulse test circuit, and for driving that, typically we use resistive gate driver. But resistive gate driver, if you go at high switching frequency, the loss in the gate driver is high, and the power supply required for driving that gate driver is also high. So how can we reduce the loss in the gate driver side? So for that, we can use resonant based gate drive. In this, we use the inductance of the circuit and the capacitance of the device as an LC resonant tank, and use this to turn on and turn off the MOSFET. So let's say the very basic circuit for resonant gate drive is shown in this figure. So when so here VG is shown as a DC source. Basically, it is a pulsating waveform, which is the drive for the gate drive circuit. It is shown as a DC source here just because we are trying to explain operation of when we want to turn this device on. And the MOSFET is modeled as a capacitor here. Okay, so when we get a high pulse, when we get a rising pulse on the VG, what we can do, we can turn on S1. If S1 is turned on, L and C will resonate according to these equations. So voltage across the capacitor and current through the capacitor equation. Those equations are given. So basically what happens, current earlier it was 0, and it will slowly increase up to a maximum, and then it will decrease. Okay, now if this is the if there is no diode D1, what will happen? Current can go negative also. So the purpose of D1 is to not make this current go negative when we are trying to turn this on. And the voltage across the capacitor is shown in this figure like this. So it's a cosine form. So the C dV by dt is current. So the integration of current is voltage. So and minus V1 is the earlier the voltage across the capacitor when it is off. When the switch was off, the voltage across the capacitor is minus V1, and then it's a cosine wave, and it will reach up to V2. Okay, and then V2, and the difference between V1 and V2 should be 2 times of VG. So if minus V1 is equal to 0, if it was discharged, so it will go up to 2 times of VG. V2 will be 2 times of VG. That's the principle of resonance. Okay, and the reverse process happens when we want to turn off. So when we want to turn off, what will happen? We get a VG as minus, and then we turn on S2. Okay, so this is the operation of a resonant gate drive circuit. Now in a silicon carbide MOSFET, so now here what we did, the capacitor is replaced with a MOSFET. And the silicon carbide MOSFET, the typical requirement is that When we turn this on, it should get plus 20 volt, and when we turn this off, typically it is minus 5 volt or minus 3 volt depending upon the switch. If we talk about IGBT, the turn on voltage is plus 15, turn off voltage is minus 15. So plus V and minus V both are equal. But here plus V, when we turn on, it is 20 volt, and when we turn off, it is minus 5 volt. So that is why we have to have three voltage sources in such a way that if VA is 12.5, VG will be 7.5, and VB will be 5 volts. So VG plus VB in this case will be 12.5, and the inductor is connected between VA and VG. So if we consider the voltage across VA, it is 12.5, and VG and VB is also 12.5. The next slide, it will get clear. Okay. So in this way, we have to have supply arrangement. Now, what about S2 and S4? So typically, when the resonance gets over, the capacitor is open. There is no, if it is open, and because of resistance in LR and diode and switch resistance, it may not be clamped to 20 volts. So what we do in this case, when the resonance gets over, we turn on S2, and whatever extra charge needed for this capacitor to reach to 20 volt, it is supplied by RB, D2 and S2. So for that part, we are doing the resistive gate drive circuit. Otherwise, it's a resonant gate drive circuit. And the reverse will happen in case of turn off. So S4, D4 and RA will connect this to minus VB. So the detailed circuit is shown here. It is like this. So when the S1 is at the time of turn on, we turn on the S1, and LR and CISS will resonate, and the voltage, let's say, reaches to plus 17 volts. It won't reach to plus 20 because of some drop in the resistance in the, or parasitic resistance, etc. Okay, and after that we turn on S2, and then the current flows from RB, D2 and S2 and charges the capacitor to plus 20 volts. And then we keep this switch S2 on for the remaining duration of turn on. And when we want to turn off, we turn off S2 and turn on S3. The reverse process will happen. I haven't shown the reverse process, but the same thing can be explained. The reverse process can be explained in a similar way, the turn off process. Okay. But as you can see here, we need three power supplies. Okay, but typically what is available to us, power supply for positive and a power supply for negative. So we will be having 20 volt and minus 5 volt power supply. So how will we generate this plus 7.5 etc.? So for that we have created a capacitor divider and connected the midpoint or midpoint of the capacitor to the resonant circuit. So we have to choose CA and CB in such a way that voltage across CA will be 12.5 and voltage across CB will be 7.5, and VCC will be 20 volts in our case, and VEE will be minus 5 volts. Okay, so in this way we have created the split power supply using a capacitor divider. Okay, And then how do we generate the pulses? So for these four switches, so for this there is a differentiator R2, C2 and R3. They form a differentiator. So whenever there is a change in the pulse, um, that will turn on S1 or S3 depending upon rising edge or falling edge. If it is a rising edge, S1 is turned on because it's a NPN transistor. If it is a falling edge, then S3 will be turned on because it's a PNP. So the R2, C2 and R3 should be chosen in such a way that they keep these two switch, S1 and S3 on for the total resonant time. So that we have to tune properly. And once the resonance period is over, the differentiator will also make sure that S1 and S3 are off. And then R1 and C1, they are a low pass filter. So it will turn on S2 and S4 accordingly after some time. So when the resonance is happening, S1 is on, and when resonance is over, uh, S2 will be on. And this timing has to be arranged from this R2, C2, R3 and R1 and C1. So this is the very important part of the circuit. So this is the overall circuit which we have made. So we have an air core inductor, and this is the MOSFET, and the diode is here on the bottom side, and these are the field capacitors. So this is a double pulse test circuit which we had made using resonant gate drive circuit. Okay, and these are the typical turn on and turn off waveforms. So you can see the turn off is very fast, 20 milliseconds we are reaching, sorry, 20 nanoseconds we are going from 0 to 600 in 20 nanoseconds. The turn on is slow, it's approximately 30 nanoseconds when it is going from 600 to 0. So, but we can change the speed of turn on and turn off if we split this LR in two ways, and one LR will be in series with D1 and another resonant inductor will be in series with D3, and the value of these inductors can be different. Then the turn on and turn off speed can be changed. Okay, and these are the results which we have achieved. Typically, conventional gate drive circuit, the power consumption was 252 milliwatt. With proposed gate driver, we reduced it to 140 milliwatt. And this includes the optocoupler IC. But if we get rid of the optocoupler IC power loss, that's 100 milliwatt, then the percentage reduction is very high, 71%. Any question on this before I proceed further on the silicon carbide based inverter and grid control for that? I think you are in mute.
Ram, what I'm saying is you can finish and then we can come back.
Okay. So then we have developed a two-level inverter using silicon carbide MOSFET-based silicon carbide MOSFET-based converter. So this one we have switched at 50 kilohertz. The main advantage is reduce current ripple heights and improve thermal management, increase efficiency, etc., etc. And so basically this one we have developed in our lab. But before coming to India, I was working in Albo on the same converter. and there we have developed another setup, and that we had connected to grid. Okay, so if there is a silicon device based converter, typically we use an LCL filter. Okay, and the the typical value of the inductance and the capacitor in an LCL filter is 5% to 10% for the inverter side. Grid side is 2 to 4%, and the capacitance is 10 to 15%. And typical switching frequency we keep up to 20 kilohertz or so. But when we go for silicon carbide based converter, we can go for very high switching frequency of 50 kilohertz. And then even with 1% inductor, we can achieve our requirement of 5% PHP. So the main advantage is size of inductor is reduced here. Now, size of inductor is reduced. That has and very switching frequency has increased. If the switching frequency has increased, we can increase the current control loop bandwidth. Typically, the thumb rule says the current control loop bandwidth should be 1/10 of the switching frequency. That's the typical thumb rule. If we are switching at 10 kilohertz, we keep at 1 kilohertz. We keep the current control loop bandwidth as 1 kilohertz. For 50 kilohertz, we can go up to 5 kilohertz. So now we have a pretty much huge separation between the corner frequency of this RL and the current control bandwidth, 5 kilohertz. So that has a very important or a very crucial advantage in terms of the control of negative sequence current, which I'll discuss in the following slide. So typically we have current primary control of current control in synchronously rotating reference frame. Okay, our DQ reference frame. So current is split into D and Q component, and then we get the D axis current component reference from the outer DC link voltage controller. Now here D axis is aligned with voltage vector. So in that case, this is the typical block diagram of the controller. Now we feed forward omega LISQ term. So, and if we assume that the gain of the inverter is 1, or we scale down omega LISQ by gain of the inverter, this whole block diagram will reduce to this. Okay. Now if we use internal model of IMC, internal model PI controller design, internal IMC, internal model control, then if I use GC as, if the PI controller is designed as this function, omega C RF plus LFS divided by GIS, the open loop transfer function becomes omega C by S. Okay, so GI and GI will get cancelled, RF plus LFS get cancelled here, so we are left with omega C by S. So that is the open loop transfer function. What is the closed loop transfer function of ID to ID reference? If we keep disturbance to be 0, that is 1 upon 1 plus S by omega C. Now this omega C is our corner frequency of ID reference to ID transfer function. If the switching frequency is 10 kilohertz, typically we choose this omega C as 1 kilohertz. If it is 50 kilohertz, typically we take it as 5 kilohertz. Okay, we can go even higher. Okay, but the thumb rule is we keep at 1/10 of the switching frequency or the sampling frequency. Now, if we keep this as ID by ID reference, what is the effect of grid voltage variation on ID? Okay, so the transfer function of ID versus ED is 1 upon GCGI into 1 upon 1 plus S by omega C. Okay, so this is 1 upon the PI controller with ID reference variation is 0. Now this transfer function is a PI controller. 1 upon GIS is GCS is a PI controller. If ED is DC, for DC this transfer function is 0. For DC this transfer function is 0. So ID will be 0. If there is any disturbance, DC disturbance, it will not reflect in the ID. But typically, in case of grid unbalance, ED can have positive sequence and negative sequence. If it has positive sequence only, then ED is DC. But if it has positive as well as negative sequence, then ED can have a 100 Hertz component. So that 100 Hertz component will create 100 Hertz ripple at the ID. Okay, but typically what we want a balanced grid current. So in that case, ID should be a pure DC value. It should not have any 100 Hertz ripple. So what we can do, we can sample a grid voltage, pass through a high pass filter, get the 100 Hertz component, multiply with a gain, and add as a feed forward term. Okay. Now the important part, you remember I said that because we can go at very high corner frequency of the current controller, the ID by ED Bode plot for silicon carbide MOSFET-based grid-connected converter switching at 50 kilohertz, current controller designed at 5 kilohertz will look something like this. So you can see a two corner frequency. Okay, one is omega C, that is 5 kilohertz. Another is well below 1 hertz. So we have a huge segregation between these, and the disturbance in ED is at 100 hertz, somewhere here. Okay, so for 100 hertz, it is like a DC. Okay, so ID by ED is proportional to, it is proportional to a constant value depending upon the gain of this and the gain of the transfer function. Okay, and we have taken that as an advantage and control the grid current by changing the value of K. Okay, now if I choose K equal to 1, then whatever be the disturbance in this will be rejected. Okay, and then I'll get a pure balanced grid current. Then we have taken another situation where we are drawing high current from the phase which has high voltage. So this grid connected converter was working as a rectifier. It was drawing power from the grid. So in that case, what we were trying to do, if there is a phase which has high voltage, there is a assumption that that phase is lightly loaded. So we should draw more amount of power from that phase compared to other phases, and this way we can try to balance the grid voltage or support the grid. So that can be done by changing the K value, and that is shown in this figure. We have taken some arbitrary number for K just to show that we can draw high current from the phase which has high voltage. How much should be the reference, that needs another study, that how much we should draw from the phase which has the highest voltage. And we have assumed 2% unbalance in the grid in this scenario. And then you can see that the DC link voltage will have a huge ripple. Okay. So these are the two things which we have done on silicon carbide based converters. If you have any question, yeah, you can ask me.
So so what we can do is that we can probably like go one by one and we can see if people have some doubt, huh? So maybe we can start with some of my students are also sitting here, so maybe they can start if they have any question.
Yeah.
And we can go to Professor Padi's student who are also there.
Yeah.
So you guys have any question you want to ask? Good. We can listen to you.
Hello, sir.
Yeah.
Sir, the two-level converter that you have built in the lab.
Yes, this one.
Yeah. What was its power rating?
We have used 30 ampere switch, and we have tested it up to 5 kilowatt.
Okay.
And if the switching frequency is limited to 10 kilohertz or 20 kilohertz, we can go up to 10 kilowatt. For 50 kilohertz, we can say that safely operate up to 5 kilowatt because heat sink limitation. And if you want to reach 10 kilowatt with this, it is doable, but the heat sink should be replaced.
Okay. And sir, you drive this converter by DSP or some displays or something?
DSP. We use right now 28335 DSP. And you can see these three black terminals. These three black, can you see?
Yeah, I'm seeing, sir.
Yeah, so those are optical fiber interface.
Okay, okay.
So that optical fiber interface is coming from our DSP. So we have a transmitter in DSP board, and then we have put a receiver on this.
Okay, thank you, sir.
Okay.
Hello, sir.
Yeah.
Sir, in that voltage unbalanced case, sir.
Here.
Sir, this the scheme will work even if the percentage of voltage disturbance is more than 2%, right, sir?
Yeah, it will work. It will work.
And sir, if there is a phase difference in the grid side, then sir?
Phase difference in the
grid side, like unbalanced in phase.
Unbalanced in
Phase.
That has we have not tried that.
Yes,
Of course, if there is an unbalance in the phase, but you mean to say there is a negative sequence as well as phase in that negative sequence. Is that what you mean?
Yes, sir.
Yeah, it will work because similarly you should have VGQ also. Okay.
No, sir. I meant, sir, like VA is at 0 degree, VB is at, let's say, minus 125 degree, and VC is at minus 242 degrees, like that.
Yeah, it will work. It will work. It should work. It has to be tested. I have not demonstrated it under that condition, but it should be working on that.
Good afternoon, sir.
Good afternoon.
So in that figure file showed that the inductor size has been reduced to 1%.
Yes.
I think 17. Yes.
Yeah.
And you are in place of LCL filter, you are using only L filter.
Only L filter, yes.
So I'm asking that will that be sufficient for meeting all the EMI conditions for the grid?
No, no. That's not an EMI filter. LCL filter is not an EMI filter. It's it will just reduce the TSD by 5%, and the definition of that TSD is up to 40th harmonic.
Okay. So you will be using an external EMI filter.
External EMI filter is required. Yes.
Okay. Thank you.
So I think Professor Padi's students are also there, so maybe they can ask, and then I also have few questions. You guys can hear us?
Yes, sir, we can hear.
Yeah, so you want to ask something, Professor Ram, regarding this?
Sir, like, have you tested with a different short circuit ratio of the grid?
No.
Because anyhow, it will add up with the inductance of whatever inductance you add.
Yes.
So, because definitely it will have some impact on
Yes.
the control strategy.
Yes. It has not been tested on that condition. So
Okay.
that's a good input. We can do some additional testing on different, different kind of grids, weak grid, strong grid, because the value of inductance changes when you have this situation, and that affects the performance.
Yes, sir.
Yes. So that is not yet done.
Anything else?
Thank you.
Okay. Anybody else from your group want to ask something?
No, sir.
Okay. Ram, I have a few questions, mostly related to the first part of your presentation. So, one was you have shown this capacitor divider circuit, right? Yeah.
Yes.
You're dividing using capacitor. So, in this case, if I correctly understand, if there's the average current through the inductor should be 0 for these voltages to remain balanced, right?
Yes. And
so was that something you observed in the experimentation?
That we have shown in the paper, that the average current is 0. With this scheme, we have shown that in the paper. Maybe I will share that paper. It's there in that.
Sure. Yeah, because that was interesting to use capacitor divider and then mention that.
Yeah.
Other thing is also
one more thing. The capacitance value should also have a certain ratio. That so those equations I have not put in this, so that it becomes simpler for presentation. But those information can be found in the paper.
Right. Yeah. So other thing was that you showed one result where the turn on time was, I mean, that was not the full turn on time, but then the rise time for the voltage is much lesser than the fall time of the voltage.
Yeah.
So why is that? Because if we are using same inductance, and if the voltage, if the forcing function is also same, that means we are applying same delta V. That I don't know if it is same or not. Then C being same, then it should sort of more or less be same, right? But here it looks like it is.
It's different.
Yeah.
We are not sure why it was that. Maybe that the input capacitance was different for different voltage, so that can be an effect. That can be one possibility of that.
Right.
So
yeah, I think that may also be possible. Yeah, that is the only
input. The different input capacitance are different in DC-link voltage or
MOS capacitance, you mean, right?
Yeah.
Voltage, the MOS capacitance is.
Yeah.
And moreover, it has some kind of other effect.
Non-linear characteristics.
Also, one thing which, like, just because you have been doing it just from the experience, so silicon inverter that you have created, have you sort of tried to do some measurements which can show what is the composition of switching loss and what is the composition of what is the value of switching loss versus conduction loss happening in the devices? Like, did you do some measurements? So
no.
we can.
You mean to say at various frequency what are the losses, and then we can say.
Yeah, maybe doing that plus doing some IV, like putting some probes and then measuring the on and off characteristics and then calculating things based on that. Plus, what you are saying is also correct, that we can probably run it at different frequencies.
Yeah.
And okay.
That has not been done. So we are buying a power analyzer. And once we have that, then we can compare the efficiency of this converter with silicon and at various frequency also. Right now, what measurements we have. So after this converter, this converter we have built for electric vehicle application, okay, for motor drive basically. And after this, we have put an LC filter. So we have some measurement of the power output at the LC filter and input power at the DC lane. Not the, so it has efficiency of inverter plus LC filter, not only the inverter. Because the power laser which we had works good for 50 hertz, not for high frequency. So now we are planning to buy one, Yokogawa WT 5000, and then we can do those things.
Right. Okay.